Hello everyone, my name is Burak Karaduman. Today I am going to talk about future of intelligent agents. A production line system is given as a case study. In each 8.5 years, a new programming paradigm is coined to be used by the practitioners and developers. But this brings to ask this question to our minds: what is the role of the intelligent agents for the next 10 years? Because so far most of the programming languages were implemented as either compliant or interpreted one, but we foresee that the future of the intelligent programming is going to be about hybrid languages. And why is that so? Because the requirements of today's systems are quite complex. Once we consider the explainability of the system to trace the decision-making path of it, it should be transparent as much as possible. And uncertainty handling is an important aspect to handle the uncertainty that may occur during the runtime of the system because of the physical environmental events. And reasoning is also an important aspect because the system should reason about its environment and events that happen in this environment. And also decision making is also important criterion to assess multiple inputs and multiple criteria. Context awareness is also a point that the system should be aware of its context and the data that should be gathered and harnessed or fusioned to provide a better input interpretation. And self-adaptation is also a degree of adapting itself. In case of emergencies or unwanted situations, the system may switch to alternative behavior or reduce its behavior to adapt the situation. And proactivity can also be interpreted as a degree of intelligence. The system should take initiatives to achieve the highest utility. So once we look at the literature, we can see that the multi-agent systems are good match to meet these requirements. And let's assume that we have a system and multi-agent systems as the autonomous entities and intelligent beings. They are added to the system as another layer. And here in this presentation, we call intelligent agents as an umbrella term for describing agentic AI, physical AI, BDI agents, and rational agents. And BDI refers to the belief, desire, and intention agents, which is quite a human-centric reasoning mechanism to implement intelligent agents. Once we look at the industrial perspective, we can see that there are two types of intelligent agents. Actually, simple reflex agents can only claim the partial intelligence, but actually they are self-organized system which can organize themselves according to the uncertain events, but they are getting quite old-fashioned because these simple reflex agents are actually simple on-off control based autonomous entities. They are controlled based on some thresholds, and if that threshold is exceeded, then they simply match a behavioral pattern with the input to produce a single output. But they do not have any reasoning or planning mechanism to further meet the requirements of today's systems. But on the other hand, intelligent agents are quite goal-based advanced control mechanisms. They also have reasoning abilities and they can provide planning features. Here, planning means that there are many ways of doing a single input based on the dynamic context. If context is changing in an environment where the system is placed in, the system can check the context and select different plannings to achieve the same goal. But we should, of course, not put the simple reflex agents to the trash because they were quite handy so far. At first, they became famous with the Grace project. And then, thanks to the Goodman project, they were adapted to the use of the industrial area. But for now, for the future, what we can do, we propose that we should switch from simple reflex agents to the intelligent agents and look at the EU projects of the intelligent agents. At first, Mass for AI was initiated by Germany to use the intelligent agents to be used by the industrial area, especially for manufacturing domain. And also Netherlands initiated Open Agri project for agriculture domain. Spain also followed the same. And then Sweden created the Disinma project for their use, and there is also Ensure project from Turkey to use the intelligent agents for autonomous cars. And United Kingdom and also Sweden put forward the Whitemac and Taylor projects respectively to create self-explainable, autonomous, optimized intelligent agents. The fundamental studies are also initiated by these countries. And while talking about these countries, they are neighbor countries of Belgium, but unfortunately, Belgium is not a project initiator for this domain. But fortunately, these projects are actually quite theoretical oriented, and they propose to use fuzzy logic as an extension to deal with the uncertainties. So this fuzzy logic is going to be explained further in the later slides. And if you ask about how much cost spent on these projects in total, approximately 30 millions. Let's hear more about today and the future of these systems. Once we look at this Gartner chart, it shows that there is an AI agency gap between low agency and high agency. Low agency refers to the simple reflex agents that I just explained, and high agency turns for intelligent agents and also the intelligent agents extensions. And also another Gartner chart shows that autonomous agents and multi-agent systems are going to be the next hype for the next 5 to 10 years. How about the industrial perspective? If we look at the industrial perspective, we can see that NVIDIA and Siemens, they have already started using the intelligent agents. Now, NVIDIA foresees that the development of intelligent agents are extended as agentic AI and physical AI. And also Siemens proposed to use the Agent Studio as a tool to define the requirements and development of their projects. And their projects are handled by multi-agent systems. And they also support these developments and requirements elicitation process supported by domain-specific modeling languages. And their also work and implementations can be described by SysML principles. But the thing is that they focus on the system design. They only provide basic intelligent agent support, and they do not aim to use cyber physical systems, or they do not provide any enhanced features yet. Once we look at both industrial and research hands, we can see that both perspectives are overlapping. However, they miss uncertainty handling and enhancements that can be provided to extend the intelligent agents, especially for the physical AI. So what we have done for this purpose, we enhance the reasoning mechanism and perceptions and actions of the intelligent agents. But in an ideal world where the initial state is proposed, as shown on the left-hand side of the presentation, let's say that we want to achieve the goal state as it is shown by the right-hand side of the presentation. And the intelligent agents can perform some actions by selecting the plans to reach from initial state to goal state. Of course, this is a pure simulation environment where the Alice is in the wonderlands, in other words, in an ideal world. But the problem is that the real world is not like this. It is more complex and uncertain compared to the simulation environment. For example, the figure on the left-hand side shows that there is the sun shining and there is some winter season, and if I ask that if the temperature is less than 32 degrees in Celsius, then I can say that maybe I should wear a snow jacket. But the problem is that in a more uncertain situation, like the figure uh, describes on the right hand side, let's say the sun is still shining, the hurricane is about to come, and there is also some wild wind, and also the winter is still winter. But the problem is that I am going to experience more parameters. I should consider more conditions. So in this situation, we cannot use the traditional logic or conventional systems to deal with this uncertainty. Instead, we need an enhancement, and we should switch from traditional logic to more updated one, named fuzzy logic, to deal with the uncertainty. And of course, how do we achieve this fuzzification process for the intelligent or BDI agents? At first, we have a domain expert, and this domain expert can be an operator in our research team or industrial environment. But this person is full with the knowledge that we require. However, this person can also leave from our domain anytime, and we may lose the knowledge. So we extract the knowledge from this person, and we create our knowledge base, and then based on this knowledge base, we create our system rules, and these rules are actually transformed to the plans of the intelligent agents. Once we deploy this fuzzy enhanced intelligent agents to the system, like in a way like a multi-agent intelligent or fuzzy agents, this allows us to make our system durable to the uncertainties. Even though it's a complex system, we can deploy our agents whenever we want and wherever we want. Before talking about the fuzzification process of the intelligent agents, let's have a look at their fundamental features. As the figure shows that there is a production line case study, and it consists of two layers. First layer has drop agent, shred agent, and sort agent. The layer 2, it has push agent and build agents. How it works? At first, drop agent puts a product, or in other words, Lego bricks, on the conveyor belt, and then shred agents shreds and washes this product and delivers it to the sort agent. And sort agent tries to recognize the color of this product. If the color is recognized, then it is sent to the build agent. But if the color cannot be recognized, then it is pushed outside of the conveyor belt via the push agent. Now I am going to focus on the build agent, and at the same time, as you can see, the SysML diagram can help us to represent the whole system in a modular and composable way, as the Siemens does the same. So build agent, it has an FSM-like behavior, which is easy to implement by the intelligent agents. The role of this agent is that, let's say a product color is red. It receives the first red color, then it presses it, and then it waits for the second product to arrive. It can be the same red color, or it can be any other color which is defined by its stakeholder. Then it combines two products, and the combined product is ejected outside of the system as a merged product. And the proactive operation is a degree of intelligence for intelligent agents. Here, let's say that we have a color combination where we can combine red, green, red, blue, or blue, or green combinations, and we get some points from this situation. The thing is that the intelligent agents can help us to operate them proactively. In other words, they will try to achieve the highest utility as much as possible. The thing is that intelligent agents can be used in a proactive way to achieve the red combination to get 100 points in each time as much as possible. But the problem is that, as I mentioned, the real world is not like this, and any uncertain situation may happen. As you can see that red brick is coming and the system is pressing it, the product is pressed. Then while we were expecting the second red color, blue comes as an uncertain product. So the system recognizes that this is an uncertain and unknown situation, then it ejects the blue product outside of the system, then it takes the red product, the second red product, and it merges them. In this way, 100 points are guaranteed. So this is the most prominent feature of the intelligent agents. They can behave proactively, and at the same time they can react to the situations and adapt the current context, in a condition preserving way, let's say. Of course, this is not the only way of the intelligent agents. They can also provide communication. Why communication is so important? Because, as I said, this system is quite complex and scalable. And when it comes to the scalability, and a system may consist of multiple subsystems, and each subsystem may have its own autonomy. And of course, the system can establish communication between the other agents via messaging. But the thing is that here on this configuration, each subsystem runs parallel. In other words, they are not dependent to each other. Or also, in other words, each of the subsystem has their own autonomy. But then let's say we want to switch from the parallel operation to sequential operation. But how can we do this in a traditional way? Maybe we can reprogram the entire thing or restart the system. But the thing is that this is not the thing that we want. What we really want to do is we want to switch from parallel operation to sequential operation during the runtime without any reprogramming or restarting the system. For this purpose, we can just change the plan schema or communication during the runtime. In this way, we can switch from sequential operation or to parallel operation or vice versa, or any alternative operation mode can also be added to the system. And what are the benefits of the intelligent agents compared to the simple reflex ones? Once we compared the two agent paradigms, we have seen that intelligent agents development time requires approximately 3 times less compared to the simple reflex ones. And description complexity, in other words, programming hardness of the intelligent agents is 3 times less compared to the simple reflex ones. And the intelligent agents can increase the product quality up to 40%. Of course, this experiment was achieved by two practitioners from academia and 2 practitioners or developers from the industry. And how about the fuzzy integration of the intelligent agents? We fuzzified each phase of the intelligent agents, starting from the data sampling to belief creation to plan composition or plan selection and action realization. The whole cycle, the reasoning cycle, was fuzzified. The workflow that I just provided is concretely represented here. As you can see that we have a domain expert, and domain experts tells us that there are some products which cannot be recognized by the color sensor. And the thing is that we determine these products starting from 1 to 7. There are 7 products and their colors cannot be recognized by the color sensor. Then we ask our domain expert what can be the RGB, red, green, blue rules and combinations of these products. Then domain experts helps us to extract the knowledge from that person. Then based on this, we fuzzify the knowledge that is provided by the domain expert. Then we create the rules, and then these rules are transformed as plans, and
these plans are used by the fuzzy enhanced intelligent agent. And in this way, the color sensor, which is controlled by the fuzzy intelligent agent, is enhanced in this way. And of course, this is not the only way of using the Fuzzy-BDI agents. The thing is that we can also fuzzify every every section that we want and we see feasible. For example, in a basic scenario where the two products are stuck at as shown by the above of the slide, traditional BDI agent tries to solve the stuckness problem, and as you can see, two bricks are stuck and they cannot be resolved, and they were put in a infinite loop because each time the conveyor belt starts to instantly reverse.
But the problem is that as this movement is quite simplistic and there is no other way devised by the engineer, it doesn't help us efficiently. But on the other hand, Fuzzy-BDI approaches the situation in a quite fuzzified way, let's say, because as you can see, this time three bricks were stuck at the conveyor belt. And this time, instead of instantly reversing the conveyor belt, the system starts from minimalistic to maximalistic movements by increasing the force and moving the bricks from backwards to forwards. In this way, this situation is resolved in few seconds. And also, the fuzzification process can help us to control the conveyor belt smoothly. As you can see that on the left hand side, Fuzzy-BDI controls the speed of the conveyor belt in a smooth way compared to the traditional BDI, which is shown on the right hand side of the slide. And why we may require such a smooth control? Because smooth control can help us to not to harm the products or conveyor belt itself without lowering the product quality. And we also experimented this fuzzification process, and we have seen that Fuzzy-BDI agents or fuzzy intelligent agents outperforms the classical intelligent agents up to 3 times. And this fuzzification process or fuzzy enhancement only costs 10% more computation time for us. But in the next version, in version 3, we also resolved this problem and dropped the computation time up to 2%. And of course, we do not only provide a way to implement fuzzy intelligent agents, we also provide domain-specific modeling language support, like in Siemens example. And in this way, the code generation can also be achieved to facilitate the development time and reduce the burden of the implementation process. And we can also provide Fuzzy-BDI model-based debugging tool to debug these systems. And also we can provide static analysis for Fuzzy-BDI agents. In this way, without deploying the agents directly on the system or running the code, the static analysis can be performed. And also we are getting ready for the TRL5 because we have experienced enough results for TRL level 4. So as a result, we have developed a general purpose framework for developing fuzzy intelligent agents. We have not only tested out our approach on the cyber physical systems or conveyor belt systems or production line systems, we have also experienced our tool on self-adaptive IoT systems, cleaning robots, and physics engines. And so if you are interested in trying out the fuzzy intelligent agents, we are open for collaborations. Thank you for your attention.